Welcome to the lecture on boundary conditions. So, in the last lecture in a approach towards the modeling process, we talked about the elements of modeling step, and we saw that we need to have the acquaintance with the 3 steps which we need to follow. I mean that is pre-processing, post-processing and solving. Now, once you make the geometry, then you need to apply the boundary conditions, and as it is a normally we deal with the cases of mass, momentum and heat transfer. So, we need to have the knowledge about the different type of boundary conditions which are required, which are applied on the boundaries, and other conditions, other type of boundary conditions, maybe they are of different type that we will see in this lecture, and after that the solution is the equations are solved to get the meaningful results. So, if you talk about the boundary conditions, now typically when we talk about the boundary conditions, if you typically look at the Tandy's geometry, so you have boundaries as the walls. So, you have one is your wall boundary condition. So, on the wall you will have different kind of processes going on. Like on the wall there is flow, there is shear going on, there may be roughness. So, the roughness that may also be required to be provided in many cases. So, you will have wall boundaries. Apart from that, the inlet is important, because through the inlet the material is going inside the domain. So, you have to specify that what are the inlet boundary conditions, like you may specify the velocity, you may specify the pressure. So, like that you have different ways to to represent these inlet boundary conditions. Similarly, you have exit boundary condition or outlet boundary condition. So, you have to have again the outflow boundary condition or pressure outlet or so. So, these are the options which are available to you, this which needs to be applied depending upon the type of problem we are dealing with. Apart from that, many a times we need we do the computation on a larger domain, which is time consuming. When we do the computational work, when we do the mathematical modeling or numerical modeling, that time we need to be aware that we should approach towards those methods by which you can reduce the computational time. So, that is how that is one of the parameter which is indicative of the efficiency of the computational algorithm or the computational tool or the way you are doing the computation. So, these boundary conditions like periodic boundary conditions or symmetric boundary conditions, they help you to identify those conditions and imply them in such a manner that your domain size may be smaller, and that will physically give you all the meaningful results, or that the same results which you could have done on the full geometry. Like if you have a very large vessel which is of rectangular shape, cross section. So, you will have that vessel. So, and if there is simply one inlet coming and there are 2 outlets, in that case, so if suppose you have a large Tandy's, and if suppose this is of this shape. So, suppose here. So, and so it is going like this. Now, in this case, if suppose there is one outlet which is there in the center, in that case and you have two outlets here at the symmetry plane are in the middle. Now, in this case what you can see is that you can take half of the turn disk, half along here, and do the analysis which will. So, this line has to be the symmetry on this plane. You have to apply the symmetry boundary condition, which will tell that there is the similar type of mirror geometry existing on the other side. So, accordingly your computation time will be 1/2. Again, in such kind of geometries, even you can have further bifurcation from half, because again this is the mirror geometry of this part. So, you can have the solution only for the 1/4 of the domain. So, your computational time is normally becoming 1/4 of what you are doing, and that is helpful when you are doing these analysis, when you are doing the solution of the results, when you are solving the equations, that time it becomes helpful to locate them. So, that time these periodic symmetry boundary conditions or periodic boundary conditions are also there, where periodically if you have to apply the boundary condition, in that case the periodic same type of condition, if it is applied at regular intervals, in that case you can apply the periodic boundary condition and you can get those results. So, you will have these are the different types of boundary conditions. We will discuss about them one by one. Now, the most important is the or every each one of these are important. So, first we will start with the inlet boundary condition. So, inlet is that place through which the medium of flow that will be moving, and it will be going into the domain. So, there you need to have the condition. Now, in that you may have to specify a velocity, and then you have a scalar properties of flow at the inlet boundaries. So, you can have velocity, you can have the definition of temperature or so. So, that is known as the velocity inlets. When you are specifying these velocity, then it is known as the velocity inlet condition, mostly in case of in normal case we use these velocity boundary condition, especially in the case of incompressible flow, where the density remains constant throughout, it does not vary. So, in that case you go for using these velocity inlet boundary conditions. This is not going to be suitable in the case of compressible flows. So, in compressible flows we normally go for the mass flow inlet boundary conditions, because there the density will be changing. So, that is why you go for the mass flow inlet boundary condition. So, you specify the mass flow at the inlet. You have also pressure inlet boundary. So, sometimes your pressure distribution is known, the pressure at the inlet. So, in that case you are total pressure and other scalar quantities at the flow inlet is defined. So, that is known as the pressure inlet boundary condition. So, these are the three types of inlet boundary conditions. When you go to define the inlet boundary condition, now when you are dealing with the turbulent flow, in that case you may have to go for defining. So, while discussing the turbulent parameters, that here we will also discuss that you will have to give the turbulence parameters also defined at the inlet. Especially you try to define the intensity many a times, and hydraulic dia that is also demanded required to be specified. So, you go for turbulence intensity many a times, and that will be depending upon the these are the assumptions basically. So, that is taken at the inlet. So, these are the inlet boundary condition. Similarly, if you have the exit boundary condition or outflow boundary condition. So, the outflow boundary conditions are used to model the flow exits where details of flow velocity and pressure are not known prior to the solution of flow problems. So, basically in normal case when you are defining the inlet velocity, you do not know what will be the velocity at the pressure. So, you give the outflow boundary condition, and this is the normally by default boundary condition given. So, it will take that depending upon the conservation rules, it will set the velocity or the required things at the outlet. So, that is normally the outlet boundary condition. And apart from that we also should know that there is a on the outlet you have sometimes the pressure outlet boundary condition, which will be defining the static pressure at the flow outlets. So, these are the two kinds of conditions, boundary conditions which are applied at the outlet. Now, you come to the wall boundary conditions. So, you have while we talk about the wall boundaries, you need to provide many kind of conditions, many kind of parameters, and among them you have something like wall motion conditions. There may be wall moving. So, you may specify the movement in the wall. There may be shear conditions, you may have to provide the wall shear value. Wall roughness can be provided. You may have the thermal boundary conditions at the wall. So, what is the heat flux through the wall, or whether you are providing a specific temperature at the wall. So, that will be temperature boundary condition at the wall. So, that way specification will be there. Then you have species boundary conditions also there. You have the chemical reaction boundary conditions, radiation boundary conditions. So, you have the discrete phase boundary condition, and you have the wall adhesion contact angle. So, these are the different kinds of boundary conditions for different cases. Like in chemical reaction, you can have this condition like what is the that condition at the wall also. So, whether the reaction is taking at the wall, or for the radiation boundary conditions, what will be the radiation for that wall properties need to be set. So, what will be the radiation values. So, how it will be computed, that you need to specify. Then the discrete phase boundary conditions, many a times we discuss for the discrete phase particles. So, we talk about the behavior of the discrete particle which is there, and we use many a times the Lagrangian type of method for that. And in that also you define a condition on the wall, that when this particle will be hitting the walls, what type of conditions should be given, that the wall may absorb these particles, the absorbed particle may stick to the wall, or there will be rebounding or reflecting. So, that needs to be specified on the wall. So, this is regarding the for the discrete phase kind of studies. There you need to provide these conditions. Wall adhesion contact angle. So, this is also one of the parameter which needs to be looked into. So, this is so what you see, that you have the different type of wall boundary conditions, and you need to know that what way, because suppose if you talk about the flow. So, in that case you may have the no slip boundary condition, which is mostly used. So, no slip means the layer the wall is having no movement, the wall and also the fluid layer which will be attached to that, it also does not have the movement. So, that way you apply these no slip type of conditions. So, we will talk about the different types of these wall boundary conditions. So, you go further, we go further. So, if you talk about the wall motion condition, you will have stationary wall, you may have a moving wall. So, on the moving wall also you have velocity conditions for the moving walls, you may have the translational wall motion, rotational wall motion, or wall motion based on the velocity components. Then if you talk about the shear conditions, so in that you may have the no slip condition, you may have the specified shear, and you may have the Marangoni stress, that is that stress also. So, that shear that condition is also there. So, basically if you talk about these so in the case of these specified shear, you define a certain value of the shear that is given, and in the case of these Marangoni stress in here, this is this will allow you to specify the gradient of the surface tension with respect to the temperature at the surface. So, there this Marangoni type of stress condition or that condition will be there. So, you will be getting that shear stress calculation because of these gradient of temperature on the surface. So, so that is for specified surface tension. So, so that way it is the these shear conditions are used. You have also the wall roughness conditions. So, before that we should know about the roughness parameters also are given. So, you may be encountering these terms like wall roughness. So, if the roughness is nil, then you have the no slip, so let us say plain type of condition, but there may be the roughness also provided on the wall. So, that so this roughness will be there. Then you have the temperature boundary conditions as we were discussing. So, you will have the thermal boundary conditions. Now, the thermal boundary conditions are important because while dealing with these thermal boundary conditions, you need to know that what should be the condition, proper condition which should be selected. Like you may go for the fixed temperature kind of condition, where you say that the walls are at a fixed temperature, and accordingly, because the fluid is there inside the domain and the walls are at a fixed temperature. So, the heat transfer will take place, and since the temperature of the fluid is generally higher than the wall, and walls are normally at room temperature or at some specified temperature. So, there will be heat transfer taking place through the walls, and that is to be computed. So, when you have the temperature boundary conditions provided, so in the case of temperature boundary condition which is there. So, in those cases you can find the heat transfer, and that can be found when there is temperature is fixed at the wall. So, you can have the use of the heat transfer coefficient that is local heat transfer coefficient will be there on the inner side, and based on the temperature difference between the wall and the in the fluid which is adjacent to. So, at that node which is adjacent to the wall inside the domain. So, that is being taken out. So, you will be finding that by multiplying with this local heat transfer coefficient, and then also if there is any radiation type of heat transfer, so that can be added. So, what you need to tell, you need to tell the proper temperature at the boundary or at the wall, so that the heat transfer value can be calculated. Similarly, you may have the heat flux condition. So, then apart from the temperature boundary condition where you define a temperature at the wall, you have the heat flux boundary condition. So, this boundary condition, in that you are providing a constant value of heat flux, you try to say, and from that heat flux which you provide, the solver will try or the model will try to find the temperature at. So, normally you provide these heat flux boundary condition, and it will, depending upon that heat flux. So, dividing it again by the heat transfer coefficient, and then taking into account the temperatures, you find the value of the temperature using these heat flux boundary conditions. So, you have this way different type of these typically you have heat flux boundary condition, or you have the temperature boundary condition. Then you have the convective heat transfer, then radiative heat transfer, you have the conduction heat transfer. All these depending upon the formula, these things can be applied, and you can get the you can put these boundary conditions into the model. Now, apart from that, the next type of boundary condition is the symmetry boundary conditions. So, you need to specify, as we discussed, that you specify the symmetry boundary conditions in the domain, and that basically decreases the size of the domain. So, that increases the computational efficiency, that will decrease the computational time, and so proper symmetry boundary conditions need to be applied, and also the periodic boundary condition, and that may be for the translational or the rotational type. Then after that you have so once you have put these boundary conditions, then you need to go for ensuring that what are the other things you need to know, like you have to specify the material properties. So, in fact, the material properties are specified before we apply the boundary conditions in many kind of models or CFD tools. So, you need to specify the material properties. Now, as we discussed that when you talk about these boundary conditions, so they are also they will also be depending, you must have the proper knowledge about the type of flows which you are dealing with. So, accordingly the boundary conditions will be varying, like for laminar boundary conditions you will have the different conditions, and for turbulent boundary conditions you will have the different boundary conditions and all that. So, accordingly you have to see that what kind of boundary conditions you need to apply. So, we further, so what we talked is that one of the part of the this preprocessing is that when you specify the properties, especially the material properties. So, when you specify the material properties, you have materials maybe like you have fluid, solid or porous. So, for materials normally you will have its physical properties like density, temperature, thermal conductivity, heat capacity, not temperature. So you may have these density or thermal conductivity or the heat capacity. So, these needs to be specified. Now, the issue is that they can be having a constant value, or they may be depending upon the temperature. So, you need to specify so most of the tools have this provision to have these properties defined in terms of, so that will be varying in terms of temperature. So, they will be temperature varying. So, what happens that they will be in some form, maybe there is polynomial relationship is there for the material property with temperature, or there may be a different type of forms. So, that needs to be specified while taking the properties of the material, then that will apply to all the different types of properties which is there. Then next thing which will be is that you must know that what kind of solution you are heading towards, because there is not always only the solution for the heat transfer and fluid flow. Normally you go for the reaction or the other parameters like the parameters related to the mixing of the fluid and its behavior inside the fluid, or you may have to have the conditions related to the discrete phase. So, you will have the species transport models. So, you will have to take into account that part. Then you will have the especially the discrete phase type of model will be there. So, in that you have the Eulerian Lagrangian type of Lagrangian type of model is normally adopted, where for the fluid you have the Eulerian concept, where you solve the Navier-Stokes equations, you get the velocity field and all the temperature field everywhere. And then you are solving for the discrete phase. So, that will be interacting on the basis of mass, I mean the momentum and the heat transfer interaction will be there, and accordingly you will have the behavior of these particles. So, especially they are used in the case of Tundi's when we deal with the inclusion behavior. So, in those cases these type of models are used, and in those cases you have the boundary conditions, like you have to specify the diameter of these particles and their numbers and their densities. All these things need to be specified as the boundary condition. So, because what happens that when and this is based on the concept that these particles, when they are in the existing flow field, so they will be subjected to certain forces. So, there will be force balance equation. So, basically it has its own weight and it is subjected to certain forces, and also depending upon the flow conditions which are available. So, that force balance is done, then accordingly you will have acceleration and also velocity of these. So, they will be moving in that domain, accordingly, and they will be floating or they may be going to the walls, where on the wall, as we had discussed, that you will have the condition at the wall, like it may be sticking or it may be reflecting there. So that so these these conditions need to be specified. So these are also the conditions, boundary conditions will be there for these particles which are required to be provided in the case of discrete phase. So discrete phase in those cases. Apart from that, we will also discuss in the case of Tundish flow, one thing is also common is the multiphase analysis. So what happens that you have the presence of the different phases, like you may have the gas solid interacting or gas liquid interacting or liquid solid interacting. So especially when you talk about the Tundish, in that case you have the liquid steel in the Tundish, and then you have slag there at the top. So you do the two phase or multi-phase type of analysis, and there are different methods for that. So there also you will have those analysis, and there we need to know that how this analysis used to be done, and what are the conditions which needs to be given at the interface, and how they are computed, because they are especially when we do the free surface analysis or the surface fluctuation or the interaction of the one phase with the other at the interface. So, so these there also you need to provide the conditions in the case of these multi-phase analysis, and that so appropriate boundary conditions need to be provided in those cases also. So when we will discuss about that kind of analysis, there we will study that how the appropriate boundary conditions are provided, and accordingly you get the proper output values. So in fact we talked about all these kind of possibilities of those models which we need to study, and there are boundary conditions which need to be applied in the Tundish in such cases. So we will talk about it in our coming lectures. Thank you very much.